This is Ham College episode 52 for April 30th, 2019. Ham College is brought to you by Icom. Create your own band opening with Icom's newest SDR transceiver, the IC9700, and by hamstudy.org, a great way to study for your next license exam. Good evening and welcome to another exciting episode of Ham College. I'm Professor Thomas.
And I'm Dean Martin.
And boy, we have a tough show lined up tonight. There are some tough questions in here. We're going to have a Rick-rolling time.
Yeah, we are. I predict a few buzzers going off this evening because I looked at the question pool, just kind of glanced at them earlier, and there's some tough ones in there.
There are some tough ones in there, and I can tell that you are your bandwidth compromised a little bit tonight.
I am. I'm just trying to save on the bits.
And you're not.
I'm at the.
This is. It's.
Oh wait, I'm not really there.
No, you're not.
No, I'm actually in Connecticut working for 2 weeks, so unfortunately I wasn't able to make it back in time to do the show. So. Doing it remote again.
So we've got...
So I apologize a little ahead of time for the bandwidth problem. The hotel's not doing too well this evening.
Yeah, it's Dean Headroom tonight.
That was not a good... See, I just need to keep the day job, man.
Oh, it worked. It worked good. Well, what did we talk about last month?
We talked about receivers, I believe, and yeah, and I think you gave us a math lesson on.
I did.
What was it on? I can't remember. I remember the math lesson.
Yeah, we talked about simple ways to calculate decibel power ratios in your head.
That's right, decibels.
You know,
I knew it was something like that, and apparently I wasn't paying attention or something like that.
It's a great party trick. You can impress the chicks with it, or not.
Yeah, it was pretty easy. It's a neat trick. I remember it now to kind of jog my memory.
So what are we going to talk about tonight? A variety of stuff, huh?
A lot of difficult stuff. Tubes, a lot of tubes.
A lot of tubes, some tubes.
Some electronics. Transistors, I believe, are a part of the electronics part. Mm-hmm. Although it seems like it's all electronics, really, to be honest with you.
Yeah, and we'll probably even touch on diodes, maybe standing waves. Who knows? It could go anywhere from here.
Good, and it probably will. It usually does.
It usually does. You know, anytime we're doing a live show, during the stream, there's a chat room available. That is...
Yep, AmateurLogic.TV /chat. And what is it I say pretty much every time? If you're watching the live stream and you're not in the chat room, you're only getting half the fun.
And what do I say? But which half?
Which half?
Yep.
Which half?
Which half?
Whichever half you want. But you really should partake of the whole fun experience and join us over there in the chat room.
Yeah, if you're watching live. If you're not, well, it's probably going to be kind of quiet in there.
Kind of lonely in there.
That lonely. But they feed us the answers to the questions, and we get to judge what the community thinks the correct answer to each question is. Sometimes they got it, everybody gets it right. Sometimes nobody gets it right. It's just one of those kind of things.
They got a pretty good record, though.
They do. They do. All right, well, let's get on into the questions tonight. I'll ask you the first question here.
Okay.
What are the basic components of virtually all sine wave oscillators? Is it A, an amplifier and a divider?
B, a frequency multiplier and a mixer.
C, a circulator and a filter operating in a feed-forward loop?
Or D, a filter and an amplifier operating in a feedback loop. Basic components of virtually all sine wave oscillators. I would just guess, I'm going to guess B, a frequency multiplier and a mixer. It's probably not right, but that's my guess. I really don't know the answer.
Well, let's see. Nope. Yep.
Roll that beautiful buzzer footage.
A loud buzzing sound there, and no, it's a filter and an amplifier operating in a feedback loop. And you know, I just happened to have a little discussion here to maybe help you understand this one, and some other folks.
Well, that's quite timely.
It is, isn't it? Well, let's take a look.
It's almost like you knew I was going to miss that.
What makes up a typical sine wave oscillator? Well, first let's look at an amplifier. That's the block diagram drawing for an amplifier there, that sideways triangle. You've got an input on that amplifier where you put a signal into it, and then you've got an output on it. Now, if we're talking about a feedback loop, what's going on there, this right here, some of that output is getting circulated back around into the input. That's the same effect when you've got somebody on a stage and they take a microphone and they put it in front of a speaker and you get that squeal. That's feedback. So that's actually how an oscillator works. You're feeding back some of the output to the input, and you're doing it in phase, and it just kind of becomes self-sustaining. The signal is just looping over and over, and it squeals, or it creates a tone. Now, the way you control that is you put a filter in that feedback loop there, and with that, you can tune it to whatever frequency you want the oscillator to operate at. That's basically all a sine wave oscillator is an amplifier and then a filter used in a feedback loop to send some of the output back to the input. You think you'll get that question right maybe next time? Does this explain it for you?
Yeah, it does. I'm pretty sure I'll get it right next time.
Okay. Well, I'm glad I was able to explain that one. I don't know about all of them tonight that I'll be able to explain them, but so far so good. Why don't you hit me with one?
All right, here's one for you. What determines the frequency of an LC oscillator? A, the number of stages in the counter.
B, the number of stages in the divider.
C, the inductance and capacitance in the tank circuit.
And D, the time delay of the lag circuit. What determines the frequency of an LC oscillator? Well, L stands for inductance and C stands for capacitance. So that right there tells me there's going to be an inductor and a capacitor involved in here. You know, when you put those two together, you are creating a filter. And another name that could be used is a tank circuit, which is exactly what we're using here in that feedback loop. I said we had a filter in there in the feedback loop. Well, the filter is an inductor and a capacitor, and we call it a tank circuit. So I'm going to say it's C. It's not a time delay in the lag circuit. It's not the number of stages in the divider, because we don't need a divider for an oscillator. And it's not the number of stages in the counter, because there's not a counter in an oscillator. So I don't know. What do you say, Tommy?
I concur, Professor.
And everybody over in the chat room saying it's C. So I think I'm safe.
The LC was the kind of the giveaway.
That was. The tank circuit part might not have been, but inductance and capacitance. So another one for you. Which element of a triode vacuum tube is used to regulate the flow of electrons between cathode and plate? Is it A, a control grid?
B, heater?
C, screen grid?
Or D, trigger electrode? I think, which element of a triode vacuum tube is used to regulate the flow of electrons between the cathode and the plate? I think it's going to be A, the control grid, Professor.
You don't think it's heater or screen grid or trigger?
I just don't think so. I'm not the foremost expert on tubes, but I do remember a little bit about the grid. I just think that's it. I don't know. I mean, that's not my area of expertise, unfortunately, but that's what I think the answer is.
Okay, well, we've got some A's
apparently,
and we've got some C's.
Screen grid. Now I'm second guessing, is it screen grid or control grid?
Well, get your answers in while it's still hot.
I'm gonna change to C, Charlie, screen grid.
Okay. Email is really.
I'm still probably going to get it wrong. Huh?
Email is really enjoying the episode tonight.
Wow, man. Wait, hold on, I'm breaking up. I'm about to drop out.
More buzzer action.
The bandwidth. Look.
Bad bandwidth. Should I explain this? Maybe.
Yeah.
Maybe because there are other folks that had the wrong answer as well.
Well, I've done hardly anything with tubes ever.
All right.
And when I studied this stuff, what was it, like 15 years ago?
Yep. All right. Well, let me give you your first hint here. Triode. Tri means three, right?
Okay.
All right. So there's three elements in that tube. The anode,
the
cathode, and the control grid. And the filament, we don't really count it as an element. In some tubes, the filament and the cathode are the same. They use the filament itself as the cathode. So there's three elements in there that are really active: anode, cathode, and the control grid. So there is no screen grid in a triode. That's the key right there. There's only three elements in that tube, so there could not be a screen grid. The screen grid could have some effect. Now, in this case, no, there's not a screen grid there to have any effect on regulating anything.
Well, that's two buzzers I've gotten so far tonight.
Well, I'm
not answering any more questions.
I got a lot to catch up then.
Yeah, sometimes I'd like to just study before these things, but I guess that kind of take all the entertainment value out of it.
Well, it does, but we do recommend that you study before you take your exam.
Yeah, but I've already taken mine, so. Yeah.
Okay. Well, then ask me one.
Okay. Which I feel like I'm under the 8 ball here. Which of the following solid state devices is most like a vacuum tube in its general operating characteristics? A bipolar transistor.
B, a field effect transistor.
Or C, a tunnel diode.
Or D, a varistor. Which of the following solid-state devices is most like a vacuum tube in its general operating characteristics? Well, a varistor, that's not it. A varistor is not it. I don't really want to say what it is and give away anything here, but
I think I might know what this one is.
what is a varistor then?
No, I think I know what the answer is.
Okay. And it's not it's not a tunnel diode, because it's nothing like a vacuum tube, just like a varistor is not.
But when electronics progressed, didn't tubes kind of got replaced by transistors, right? So that kind of...
Well, they did. They did, in effect. I mean, there's still tubes out there, but in most applications, yeah, transistors replace them. So we know it's either a bipolar transistor or a field effect transistor. And this is not your question. Just go ahead and take a guess, though. Just, if you want.
I'm pretty sure it's B.
B, a field effect transistor. I'm going to agree with you. And, oh, boy, the chat room does over there. They're like, everybody's saying B, so that's got to be the answer, right?
Yeah, should be.
Field effect transistor. There you go. It operates the most like a vacuum tube out of all the devices we mentioned there. So, you could possibly choose a bipolar transistor there. So that's, that could be a little bit tough.
Yeah.
Okay, I've got one more question here that I think you'll get this one right. What is
Maybe.
What is the primary purpose of a screen grid and a vacuum tube? Is it A, to reduce grid to plate capacitance?
B, to increase efficiency.
C, to increase the control grid resistance?
Or D, to decrease plate resistance. I don't know that I'm going to get this one right or not.
What is the primary purpose of a screen grid and a vacuum tube?
I'm going to guess A. I think it's going to be A.
Okay, that's what the folks in the chat room say.
Resistance, capacitance, increase efficiency. I would assume that's something to do with capacitance. So I'm going to guess A.
Okay, I think you're probably onto something there. Everyone in the chat room saying A.
But I hope you're going to explain it. You got some explaining to do, if that's it?
Well, I've got a little bit of explaining to do, yeah. And that is it.
That was it.
So let's actually look at a tube that's got a screen grid in it. Just happen to have one right here.
Wow.
Yep.
That's quite a coincidence.
This is called a tetrode. It's got an anode, a cathode, a control grid, and a screen grid. And, we could talk about how a tube works, but, I don't have all my arrows and drawings out here ready to explain that tonight. I think we've probably done it here before. Essentially, you've got electrons flowing off of that cathode going toward the anode. They would be just running wide open if those grids weren't in the middle there. The control grid is what more or less regulates the flow of electrons from cathode to anode. And then the screen grid is in there, helps to reduce the grid to plate capacitance, because there's some capacitance between that control grid and the plate. The plate is the anode. Plate and anode are the same thing. So putting that grid in between the two helps reduce the capacitance that's inherent, when two pieces of metal are near each other. It can help improve the gain of that tube. It could possibly help suppress the tendency to have some oscillations in it. But the main thing I wanted to show here is a tetrode is a tube with 4 elements in it, and that's where the screen grid is located, between the control grid and the anode, or the plate.
Makes me realize how little I know about tubes.
Tubes are fun. As a matter of fact, you should probably be carrying around some in your suitcase there, just to have something to play with.
But while I'm sitting here at the hotel.
Exactly.
Yeah, maybe I should see about getting some of those at the Hamfest. Well, it's interesting. It's really interesting what they can do, that little tube of glass and stuff, and it's pretty. But anyway, I just really never really got into them that much.
Well, I have done a video on Teebs before, and basically how they work. Maybe we ought to pull that back out and look at it in a future episode here, because it's always good to kind of refresh on that kind of stuff.
Yeah, maybe we should have done it before we did this.
Maybe we could have done it tonight, huh? Yeah.
It would have been a good time.
Okay, well, we're going to take a quick break and come right back, because we've got more questions to go yet. Create your own band opening with the IC9700. Icom's newest SDR transceiver, the IC9700, this new radio is bringing direct sampling to the UHF-VHF weak signal world. The IC9700 all-mode transceiver is loaded with innovative features, such as dedicated amateur satellite operation, color touchscreen, built-in D-Star capability, RF direct sampling on 2 meters and 70 centimeter bands, dual independent receivers capable of full duplex operation as well as dual watch, 100 watts maximum output power on 2 meters, 75 watts max on 70 centimeters, and 10 watts max on 1.2 gigahertz. Visit IcomAmerica.com/amateur for more information on all the great Icom radios. Attention all hams. Icom knows that ham clubs play a big role in bringing ham communities together to learn from their peers and industry leaders. As a way to give back and help you on your mission, Icom has launched a promotion exclusively for U.S. ham clubs and the Hamfest they're involved with. By registering your club, you could win Icom swag, a Skype presentation for your club, or your Hamfest, an Icom booth setup. Register today for your chance to win at IcomAmerica.com/hams. Pack your bags, because Dayton Hamvention is coming up from May 17th through 19th at the Greene County Fairgrounds and Expo Center in Xenia, Ohio. See the latest and greatest Icom gear and meet hams from all over the world. You know, Icom is giving away some swag kits. As a matter of fact, let me look here. I don't know if they look exactly like this one, but remember these are the swag kits they were giving away at Hamvention last year.
Yeah.
They're giving those away again this year. If you register and happen to win, you've got to be attending Hamvention to actually pick up one of these yourself and win. So if you're going to Hamvention, what you need to do is go to IcomAmerica.com/amateur and register right there to win one of these great swag prize kits. There's a lot of good stuff in here. I know last year there was a hat, there was a t-shirt, a water bottle, a badge, and a lanyard. I don't know what's going to be in this year's swag kit, but they're going to be giving them away, and they're taking registrations right now. IcomAmerica.com/amateur. Get your name in the hat today if you're going to Hamvention. If you're not, then and you registered, the swag kit you got is likely you're not going to pick it up at Hamvention, and it's going to be in a box sitting right behind our desk here on Ham College. I have a box of these back here from 2018 that we got to figure out some way to give these away, Tommy. They're ones that people didn't pick up last year. So Ray was here, this past week. We were shooting videos on some new radios, and I got a big box of these that we'll be giving away in the future. But you really want
good swag gifts for somebody.
Yeah. You really want a 2019 version, though, if you're going to Hamvention, IcomAmerica.com/amateur. And we do a contest here every month on Ham College. We've got some actual swag prizes that we use right here. How can you win in that contest if you would like to?
But we've got a strict set of requirements that you've got to meet to be able to be in the contest. You've got to have a name and you got to have an email address. But other than that, you're pretty much wide open. Send an email to hamcollege@AmateurLogic.TV and you'll get entered into the drawing. If you don't happen to win this month, I know you're dying to hold that up there. If you don't win this month, hey, that's perfect fit too, man.
Yeah.
Anyway, if you don't happen to win this month, be sure to enter again for next month because the pool gets cleared out each time, so we start over from scratch.
So what could they win?
You can win this hat I've got on right here, and and the T-shirt that's laying right there.
This one?
Yeah, this one right here.
The Icom Ham Crew T-shirt.
Nice ham. Yeah, go ahead. Sorry.
Yeah, I was just interrupting you. You could win the nice Icom Ham Crew T-shirt and Tommy's hat.
And Tommy's hat.
And whatever else Jesse can stick in the box. So,
yeah.
He usually sticks a few extra things in there, too. So send us an email, hamcollege@AmateurLogic.TV, and register to win. Because somebody's going to, and it might as well be you. You don't have to be a ham. Qualifications, once again there, Dean?
A name and an email address. Pretty much everybody's got those nowadays.
Pretty much.
At least the email address.
We won't be expecting an email from you if you don't have an email address. So I think most everyone here is in good shape. And as a matter of fact, we got a guy here that's in excellent shape this month. It's Jordan, W8JJB. He sent me an email. And he said, "Thank you for entering my name into the drawing. I need an Icom radio. And in lieu of a radio, I'd love a T-shirt and a hat. With spring upon us, a waterproof cap may be a better choice than a non-waterproof radio anyway. Thanks again, and keep up the great work on Ham College." Well, thank you, Jordan, and congratulations. And by the way, Icom does have waterproof radios. Not all of them, but some of them are. So
yeah, they absolutely do.
We don't have one here to give away tonight, but we will be happy to send you a hat and a T-shirt. So
I've actually got one of the older ones.
Yep. So you need to go tonight and register right after the show, because we throw away all the entries at the end of each month's drawings. And we got more questions to go here tonight. These are, I don't know that they're getting any easier.
Well, that's not very encouraging.
No, it's not. But I'll let you ask me.
I feel the bandwidth's getting a little worse again.
Yeah, I can hear you breaking up.
Yeah, it gets worse when it comes my turn to answer the question.
Well, it's your turn to ask it this time, so I'm probably coming in clear, huh?
Yeah, it's perfect right now. What is the approximate junction threshold voltage of a germanium diode? A, 0.1 volt.
B, 0.3 volts.
C, 0.7 volts.
Or D, 1 volt. What is the approximate junction threshold voltage of a germanium diode? Well, let's see if we can describe what a junction threshold voltage is. A diode's got an anode and a cathode on it. And where the two meet right there in the middle, a germanium diode is, I would say it's going to be a piece of germanium in there, and that would be a junction where the anode and the cathode meet right there. And voltage just doesn't go across that unless it reaches a certain threshold. Once the voltage is over that threshold, then it can flow right on through that diode in one direction only, since a diode only passes and electrons in one direction. It's not a bidirectional device, which is very handy for a lot of things like converting AC to DC. So what would be that junction threshold voltage in a germanium diode? Well, let's see. Boy, I hate to give this away because you're gonna get the next question coming up if I give you the answer here, but I'm going to go
just give
ahead.
the answer and then I'll take this question.
Let's think about it here. If the voltage coming in, if it's got to be at least a volt to get through that diode, then that's getting on up a little bit. If you've got to have at least a volt,
kind of high.
That does seem kind of high to me. 0.7 volts. Well, that tells you that's even a little bit higher. I know germanium diodes are used in crystal radios. They're used as radio detectors, places that you've got a real tiny voltage. As a matter of fact, it's the threshold voltage is going to be lower than in other type diodes. While I think a 0.1 volt would be great for something like a radio detector, I believe for germanium it's going to be probably 0.3 volts. I'm going to say 0.3 volts, and it's B, and that's what they're saying over in the chat room. They are saying B. So let's find out. And it is B. Can I get a fist bump on that one?
If you can run around on that side of the TV. There. Well, all right. Close enough.
Close enough. All right. Well, I'm going to ask you one here, and I feel like I've already given you the answer, but you'll get it.
I know it's not going to be 0.3.
Well, yeah, that's not it. What is the approximate junction threshold voltage of a conventional silicon diode? Is it A, 0.1 volt?
B, 0.3 volts?
C, 0.7 volts?
Or D, 1 volt? And again, I think 1 volt's probably high. And 0.3 volts was already taken.
Yeah, but you wouldn't know that if you were taking your exam. So just ignore that.
You wouldn't.
Ignore what I said about all of that.
But I don't know how you would reason this out anyway, to be honest with you. This is something I think they'll have to memorize.
Yeah.
And 1 volt or 0.1 volt seems low because of what you said about the germanium diode being one of the lower ones. So I'm going to go with C, 0.7 volts with this one.
Well, that's what everybody's saying over in the chat room. I think you're right on this one. And I would have been really disappointed if you had missed it after the lecture we just had on that. So,
yeah.
But yeah, I
was paying attention.
I'm going to tell the truth here. When I was entering these questions in for this episode, I always go through, and before I see what the answer is, to mark it right here with the highlighter, I always, quiz myself on what the answer is. I'm not sure I got this one right.
Oh, really?
Well, no, I do think I got this one right. I think it was the germanium I got wrong. I said 0.1 on it, but it was actually 0.3. So that would count as a buzzer, except nobody was watching. So
0.3 seems high if you can use that for a radio detector, like for a crystal radio. 0.3 kind of seems high to me, but I mean, obviously it's not.
No, it does seem high, but yeah, but that's what it is. So, germanium diodes are the really old ones. I mean, that's like the first type that was available in large quantities, and then we got away from those, and we started going with these silicon diodes. But there's still a reason to have a germanium diode right there, the lower threshold voltage, and they're still around. So,
yeah, that might be a fun project to do on AmateurLogic to build a crystal radio like that.
yep,
Maybe.
Well, what's next?
All right. Which of the following is an advantage of using? Huh?
I didn't say anything.
Oh, maybe I'm hearing myself come back. Occasionally, I hear myself feed back into it somehow. Which of the following is an advantage of using a Schottky diode in an RF switching circuit rather than a standard silicon diode? A. Lower capacitance.
B, lower inductance.
C. Longer switching times.
D, higher breakdown voltage.
Glad you got this one.
Yeah, which of the following is an advantage of using a Schottky diode in an RF switching circuit rather than a standard silicon diode? The advantage of a Schottky diode, and the qualifier there is we're using it in an RF switching circuit. Higher breakdown voltage? Not sure about that one. See, longer switching times. I know that would be a negative. You wouldn't like that. Lower inductance or lower capacitance? I'm inclined to say lower capacitance. That would be an advantage. But let's see.
Well, we got a lot of stuff in the chat room.
Yeah, this one's kind of tough. I can tell by they're all over the place in there. So let's just see before I try to do any explaining. Lower capacitance.
No.
That's going to be one of those things you kind of got to know, because a higher breakdown voltage sounds pretty good, doesn't it?
Yeah. Emil got it right. He said not C.
Okay. No, it's not C. I knew that much. But the lower capacitance means that that diode that you're using in your RF switching circuit is not going to have an effect at the RF frequency. So that would be the advantage there. Lower inductance. I don't know how to explain this. I'm thinking the capacitance has a bigger effect in a diode than inductance. And a Schottky diode does have lower capacitance. So
interesting. I hope that's all the diodes.
Well, let's see. Yes, it is. Why must?
Can we go back to diodes?
No, it's too late. Why must the cases of some large power transistors be insulated from ground? Is it A, to increase the beta of the transistor?
B, to improve the power dissipation capability?
C, to reduce the stray capacitance?
D, to avoid shorting the collector or drain voltage to ground? Why must the cases of some large power transistors be insulated from ground? Well, I'm going to take a wild guess here, and I'm going to go with D, to avoid shorting the collector or drain voltage to ground. So that's what the insulated from ground, increasing the beta of the transistor, improve the power dissipation. That shouldn't help being insulated from the ground. Reduce the stray capacitance. I would assume you would need to have it grounded for that. I think it's D.
I'm going to agree with you, and that's what everybody's saying over in the chat room. It's D. And there you go. You know, on a large power transistor, I should have got some out here where we could look at them. You know, they generally have a metal case on them or a metal tab, depending on the pack that it's in. And that'll often be screwed or bolted down to a heatsink, which is at ground potential. And it can be different on different transistor designs, but sometimes that metal case or that metal tab is the collector of the transistor, or the drain in the case of an FET, and you wouldn't want to short it to ground. So, good answer there, Dean.
Thank you. Did some ciphering to get to that one. Okay, what are the stable operating points for a bipolar transistor used as a switch in a logic circuit? A, its saturation and cutoff regions.
B, its active region between the cutoff and saturation regions.
C, its peak and valley current points.
Or D, its enhancement and depletion modes. What are the stable operating points for a bipolar transistor used as a switch in a logic circuit? All right, let's qualify the question here a little bit. We're talking about a bipolar transistor, just a regular old transistor with an emitter, base, and collector. And we're using it as a switch in a logic circuit. So since it's a logic circuit and it's a switch, it can either only be a high or a low. There's no in-between voltages. It's either one or the other. It's not D, it's enhancement or depletion modes. And it's not C, it's peak and valley current points. It's not B, it's active region between cutoff and saturation regions. What are cutoff and saturations? Depends on how you bias that transistor. The voltage at cutoff would be so low that the transistor is not conducting. At saturation, the voltage would be so high that the transistor, it's been saturated. It's reached its maximum. You can keep increasing what you're putting in, but it's not going to go any higher. It's just you've hit the plateau there, and it's just going to be at that level from there on out. That sounds like that would be good for a switch, because down in between the cutoff and the saturation regions, that's where you'd operate it as an amplifier or something like that. Because once you've hit the saturation point, you could be into distortion if you were trying to amplify, say, an audio signal or an oscillator or something. But if you're making a switch, you want to make sure that that switch is all the way on or all the way off. So saturating or cutoff regions are where you want to run it. That's my logic, and I'm sticking to it. You notice how I work logic into that?
I cannot argue with that.
There you go. It's saturation and cutoff regions. That's what everybody was saying over in the chat room. So I didn't look, but I felt that's where they were going. One more question.
Well, good job. Okay.
And then we're going to take a break, and we're going to go to the snack room and come back with some more. We'll have recess.
Sounds like a plan.
Which of the following describes the construction of a MOSFET? A, the gate is formed by a backed biased junction.
B, the gate is separated from the channel with a thin insulating layer.
C, the source is separated from the drain by a thin insulating layer.
Or D, the source is formed by depositing metal on silicone.
I'm glad you got this one.
Yeah, and I was going to cheat. The chat room's all over the place. They're no help.
No, Not on that one.
Okay. Now I'm gonna have to guess. Gate is separated from the channel. Gate is formed by back biased junction. Gate is separated from the channel. Source is separated from the drain by a thin insulating layer. This one, I don't really know this one. I'm gonna this is a WAG type of guess here.
WAG, what does that stand for?
I can't say it. I'm going to guess B, but I honestly don't know. It's probably going to be buzz.
Well,
yeah. It's going to be E.
Yeah, I would say it's not D. Nobody guessed that.
Yeah, I will think that one.
But I would say that's a good guess. Can't tell you why, other than that's just the way that it is.
Oh, wow. That was just a guess.
Yeah. It was a good guess.
I had a 25% chance of getting it right.
Yeah. This is one of those things you're just going to have to know unless you sit down and do a lot of studying on MOSFETs. You good chance you won't know the answer on that. So.
Yeah, you know what? I actually saved up. Sometimes in the hotel, I get bored and I go on YouTube and I'll look up certain topics, and I actually have a few videos on MOSFET saved in my watch later thing. I probably should have watched them sooner.
Well, it didn't hurt you on this one.
I usually watch them at bedtime when I can't sleep.
Yeah. So you'll sleep through them? Is that the plan? All right. Well, let's take a little break. Let's get up, stretch our legs, go to the snack bar, and we'll be right back.
Talon Rail and Chevy.
Hey, somebody's crazy. Papa goes the weasel. Everybody knows the weasel blows, but popcorn, she pops real good. I eat popcorn. Everybody eats popcorn. She tastes real nice. Get yourself some now at our refreshment stand.
Are you new to the ham world or an existing amateur operator who wants to take your license to the next level? Study for your radio license exam at hamstudy.org. Hamstudy.org is a free online learning tool powered by Icom. It was created by Richard Bateman, KD7BBC, Michael Stufflebeam, KV9G, and Rich Porter, KK6GKE, and it uses a modern web design to enhance the experience of studying for your technician, general, and amateur extra exams. Since 2013, hamstudy.org has helped new and existing hams to familiarize themselves with the question pools, use stats-based flashcards to focus on material they need to learn, and take practice exams to gauge progress. Visit hamstudy.org on your desktop computer or mobile device. Register for a free account at hamstudy.org to access personalized study history and other site features. Prepare for an exam in an intuitive and comprehensive manner. Check out hamstudy.org, powered by Icom, for free learning tools. Good luck on your next exam. I'll let you change your answer on one there that I knew when you changed it was going to be wrong, but I went ahead and let you do it anyway. Because if you were sitting
that was awful nice of you.
Yeah, those pencils you use at the exam do have an eraser on it, so
yeah,
that happens. All right, first question here. Let's see, who asked the last one? I think I asked you, so you can ask me this one.
Oh, this is an easy one. Which of the following can be determined with a directional watt meter? A, standing wave ratio.
B, antenna front to back ratio.
C, RF interference.
Or D, radio wave propagation. Which of the following can be determined with a directional watt meter? All right, so dissecting the question, first off, a watt meter is going to measure watts. Yeah, I think that's a good assumption. And directional means it's only going to measure the watts going in one direction. That way or that way. One way or the other. So, if I can flip that direction around, though, it doesn't say I can, but let's assume I can, then I'm going to see all the power leaving my transmitter and going to my antenna as forward power. It's going in the direction I want it to go. Some of that power is going to be reflected back, though, from the antenna. That's reflected power. And reflected power is, if you got high reflected power, you got high standing waves. So you'd have a high standing wave ratio. I'm going to say it's A. It's not B, front to back ratio of an antenna. No, all you can tell with a watt meter is that watts are going back and forth on a coax, not once it leaves the antenna. You can't tell anything about RF interference with it, and radio wave propagation. You can't tell how well your antenna's propagating, or your waves are propagating from the antenna, but you can see that there's a standing wave, or the ratio of the standing waves on your antenna, or your transmission line. I'm going to say A. Everybody said A over in the chat room, so I feel like I'm safe on that one. What would you say, Dean?
Yep, I would say it's A also.
Okay, and it is A also.
A also.
Okay.
Yep.
Now let's see if I've got another question for you.
I bet you do.
Somewhat similar, but yet different. What might cause reflected power at the point where a feed line connects to an antenna? Is it A, operating an antenna at its resonant frequency?
B, using more transmitter power than an antenna can handle.
C, a difference between feed line impedance and antenna feed point impedance.
Or D, feeding the antenna with an unbalanced feed line. Well, operating an antenna at its resonant frequency. That's actually what you want to do. So that's not going to be it. What might cause reflected power at the point where the feed line connects to the antenna? So operating it at its resonant frequency is not a problem. That's what you want to do. Using more transmitter power than the antenna can handle. I don't think that's going to cause reflected power at the feed point either. Not at the feed point. Difference between the feed line impedance and the antenna feed point impedance. Well, that's where the feed line and the antenna feed point are what we're concerned with, and the impedance does have to match. Typically 50 ohms for coax fed antennas. Usually you want 50 ohm coax, or feeding the antenna with unbalanced feed line, which is totally fine. So the answer's got to be C. Difference between the feed line impedance and the antenna feed point impedance, because if they don't match, that's when you'll get a high SWR.
Okay. I am going to agree with you. I can see your logic there completely. And you're right. You're right.
All right, here you go. Here's one drawing for you. What must be done to prevent standing waves on the antenna feed line? A, the antenna feed point must be at DC ground potential.
B, the feed line must be cut to a length equal to an odd number of electrical quarter wavelengths.
C, the feed line must be cut to a length equal to an even number of physical half wavelengths.
Or D, the antenna feed point must be matched to the characteristic impedance of the feed line.
And they're trying to throw them off with some pretty wordy choices there.
What must be done to prevent standing waves on an antenna feed line? It's a pretty simple answer on that one. A, the feed point must be at DC ground potential. That doesn't matter. Although, let me say, having your feed point at DC ground potential has some definite advantages. The antenna doesn't have to be that way. It can be designed either way. B, the feed line must be cut to an equal length of odd number electrical quarter wavelengths. No, it doesn't really have to be, or even number either. I'm going to say it's D, the antenna feed point impedance must match the characteristic impedance of the feed line. This sounds almost like I'm answering the same question you had a while ago.
It's very close, but that's pretty common for them to do that.
Yep. I'm going to say it's D. Everybody in the chat room says it's D, so there we go. What standing wave ratio will result when connecting a 50 ohm line to a non-reactive load having 50 ohms impedance? Is it A, 2 to 1?
B, 1 to 1.
C, 50 to 50?
Or D, 0 to 0. But if you have a 50 ohm feed line and 50 ohm impedance, that's a perfect match. That's as good as you can get. So that's a 1 to 1. If you get one going, 50 watts going in, you got 50 watts going out. So you've got a 1 to 1 ratio there. So that's perfect. So it's going to be B, bravo, 1 to 1.
Everybody's saying B in the chat room. I agree. It's going to be B. And that's one of those questions that most people should not even stop and think about. They just know right off. A 50 ohm feed line, 50 ohm load, no reactance on it. Yeah, 1 to 1 ratio. All the power is being transferred from that feed line into the antenna.
What is the interaction between high standing wave ratio, or SWR, and transmission line loss? A, there is no interaction between transmission line loss and SWR.
B, if the transmission line is lossy, high SWR will increase the loss.
C, high SWR makes it difficult to measure transmission line loss.
Or C, high SWR reduces the relative effect of transmission line loss. What is the interaction between high standing wave ratio, SWR, and transmission line loss? All right, let's define what the question is stating there. High standing wave ratio, that means of the power we're putting back, a fair amount, or the power that we're putting toward the antenna, a fair amount is bouncing back at us. High SWR reduces the relative effect of transmission line loss. No, transmission line loss means that we're sending our power out that line, but it's being lost in the line before it ever gets to the antenna. It's not being reflected back, it's just being absorbed in the line there. So it's not D. High SWR reduces the relative effect of transmission line loss. I don't think it's C. High SWR makes it difficult to measure transmission line loss. No, it's real easy to measure it. You just put your watt meter on one side of the transmission line and then move it to the other side and see how much you lost. So doesn't change that. B, if the transmission line is lossy, high SWR will increase the loss. I'm saying it's A. There is no interaction between transmission line loss and SWR. Oh, I may be wrong. They're saying
I'm thinking it's
C
B.
and B.
What are they saying?
They're
B?
saying it's either B or C. I think so. Well, let's find out. Let's find out.
Transmission line is lossy.
I was wrong.
Hit that beautiful buzzer sound.
If the transmission line is lossy, high SWR will increase the loss. Okay, that's 3 buzzers for you there tonight. Where else can you get that kind of action?
Nowhere but here.
Okay, so forget that other thing I was saying. If the transmission line is lossy, high SWR will increase the loss. I guess it does. It says so right there.
Right there in yellow and black.
Yep. I feel somewhat embarrassed by my choice of answers there. I should have known that, but
I understand what you're feeling.
yep. You know where I'm coming from.
I do. I've been there
Well,
recently.
I've been there very recently. You know, it just seems like it just happened. Well, you know, Dayton Hamvention's coming up. Boy, it's only, what, a couple of weeks away or so from now?
3 weeks.
3 weeks? Okay. It's not far off at all. And you want to be looking good at any Hamfest you go to. And how can you do that?
Man, you should get some of the Amateur Logic or Ham College swag from the swag store. AmateurLogic.Spreadshirt.com. We've got hats, shirts, several kinds of shirts, t-shirts, golf shirts. We've got jackets, various colors and sizes. So check it out, AmateurLogic.Spreadshirt.com. If you, well, even if you don't wear it, check us out. Stop us at Hamfest if you see us. But it's always nice to see people walking around the Hamfest with the Amateur Logic swag on representing.
Yeah.
Appreciate you guys doing that.
And it's not just AmateurLogic swag there. There's Ham College swag there as well. Before we got out of here, the things that we usually mention is our social media sites. That has narrowed down a little bit, hasn't it?
Yeah, it's dwindled a little with the loss of Google Plus. So right now we've just got Facebook, Facebook.com/groups/Ham College and /AmateurLogic, I guess is the other one. And then we're also on Twitter at Ham College and at AmateurLogic.
And you can get the show notes on all the shows we do here, AmateurLogic and Ham College, at AmateurLogic.TV/wiki. Dan, N9LVS, does that for us, and we appreciate that.
Special thanks to you for doing that, Dan. He's been doing that for a long time for us. I really appreciate that.
Yep. And you can join us in the middle of May for the next AmateurLogic, and at the end of May for the next Ham College.
73, everybody. We'll see you next time.
7-3. I shouldn't even say it because it'll throw somebody off on taking their exam. But I'm going to say it anyway. If you,
I figured you were.
you could kind of feel it, couldn't you? I just couldn't hold myself back. B, the feed line must be out. I had a word wrong. From where I'm looking at it, it looks like it says out, but it says cut. So I'm going to read B again.